Hi, Assalamualaikum and good day. So, I will show you today the topic of harmonics and true power factor. This is a important topic because now in power quality we got a lot of harmonics, and harmonics cause some problem. Today we're not talking about the problem yet, but we talk about how harmonics change our previous understanding on power factor. There's a new term called true power factor. Okay, let's start. Okay, so as we learned previously, harmonics is sinusoidal components of a periodic waveform at integer multiple of fundamental frequency. Okay, so in Malaysia our fundamental frequency is 50 Hz, so harmonics might be 100 Hz, 150, 250. Okay, and the numbering of harmonics depends on that integer. For example, 150 Hz harmonics, when you divide 150 with 50, you got number 3. So 150 Hz harmonics is called as third harmonic. Okay, so that how harmonics looks like. Okay, harmonics will change the, it's not harmonics that change, it's this waveform contain harmonics. That are the waveform over there, okay, on the left hand side, that doesn't have any harmonics. That's 50 Hz. Okay, now I want to talk about power factor. We already learned that power factor is a ratio between real power and apparent power. Okay, so P over S. We know this. P is in watt. I put here 4 names of P. Active power, real power, true power, average power. It's all P. All 4 is P. Q is reactive power. Okay, the one that needed to run some load but actually doesn't produce any work. And apparent power is the vector summation of this P and Q. This is what we learned previously. And power factor, you remember power factor? Power factor we learned previously as the cos of phi, where phi is the angle between voltage and current that contribute to the same angle between the real power P and the apparent power S. Okay, that is cos phi, power factor. Okay, now when we learn about harmonics, this power factor as cos phi only true when the current is sinusoidal, when harmonics is not existent. This is like 30 years ago, there's a lot of load that doesn't produce harmonics. Our light is incandescent light. Our motor is only induction motor. Okay, no variable speed drive. Okay, but right now it will change. So what about when the current have harmonics? Okay, it's not cos phi anymore. It's other term. Okay, there are terms that we will learn as true power factor. So what does this cos phi rename as for? It's cos phi is now called as displacement power factor. Okay, when the current is distorted, then you know cos phi is not power factor, it's just displacement power factor. Okay, we will see why it's called displacement. Okay, now when you don't have that apparent power as the summation of P and Q, what is that summation, vector summation of P and Q? It's now called as fundamental apparent power. And the unit is still the same, VA, but the symbol is not S anymore, but S with 1. So we revisit power factor. Consider these two waveform. Okay, this is a linear load. Okay, so you can see there are difference between the zero crossing of voltage and zero crossing of current. And when you measure the difference, okay, or displacement, that what when you got delta t divided by t is our period, 20 millisecond in Malaysia, times 360 degree, you will get phi. Okay, so this is an example of the voltage and current that I wrote up there. Okay, and this is why this cos phi is called as displacement power factor, because it's just the displacement between current and voltage. Now, what happened here? You see the green waveform, that's the fundamental of the orange waveform. Okay, orange waveform is the total current consists of the green and harmonics. Okay, that's the total current, the green one. So as you can see, the green is not sinusoidal, it's distorted. So how does this contribute into power factor? Let's see. Okay, that current, the orange current, is actually consists of two sinusoidal waveform. One is 10 amp for the fundamental, and another one 3 harmonic. Okay, question, how do I know it's third harmonic? Because you see, the frequency of that waveform is 3 times the fundamental frequency. Instead of 2 pi ft, now it's pi ft. Okay, so this is the example that we will talk. Okay, so the fundamental component, I color it with green and yellow for the harmonics. Okay, it's important to note that for this example, there's only one component of harmonics, but in real life, there's a lot of harmonics. 20, 21, perhaps more than 20, 21, perhaps more than 100 components of harmonics. Okay, but for the simplicity of the course, I just choose one. Okay, so take a look at this linear load like induction motor. Okay, let me move a bit. All right. Okay, so induction motor have two division of the current. Okay, as you already know, the current that produce work is I cos theta, and the current that doesn't produce load is I sin theta. That's for linear load. Now, non-linear load. Okay, this is different kind of load where the current is distorted. The current can be divided into 3. For work producing load, it's still I cos theta, cos phi, but now it's I fundamental. Okay, it's important to note that. For non-work producing current, there's two other components inside that. Fundamental component is I fundamental sin phi, and now we got another component that is the harmonics component. Remember the yellow one? Okay. Okay, so this is nonlinear load current, okay, and how it contribute into the calculation of power, specifically power factor at the end. So this work producing current is still the same. It's contribute into P, so it's P equals to V I cos theta. You must remember that I is the fundamental. Non-work producing current, I fundamental fundamental current, sine theta, that contribute into Q, reactive power, V, I fundamental, sine phi. And harmonics component, okay, IH, I put a IH, it will contribute into the distortion power. This is a new kind of sort of reactive power, okay, because it doesn't produce any work, okay, but it's not displacement. So this is distortion power, okay. So let us revisit this power triangle. This is what we learned before. Now let's rotate it, okay, and then put here two other component, which is the distortion power, okay. Remember this distortion power, okay. D comes from the V times the voltage times the harmonics current, and the apparent power now is S, okay, consists of fundamental apparent power and distortion power, okay. Let's take a look at our example, okay. This current, okay, now you can calculate the total current. Total current comes from the fundamental current plus the harmonics current, okay. Of course, you need to sum this together in vector form, so it becomes 10.44 amps. P, now VI cos theta, okay, remember that I is the fundamental current, so only 10, okay, not consider this IH, not consider 3, only 10, okay. Cos theta, theta right now is 30 degree, so we come up with this number. And then Q, sine theta, also remember this must be the fundamental current, so it's become 1150 VAR. Distortion power, V times I harmonics. Now I harmonics only 3, okay, 690 VAR, okay. Fundamental apparent power, this is the summation of P and Q in vector form, okay, or you can calculate just by V I fundamental, okay, 2300 VA, okay. And S, this is the final apparent power. It's sum up of all the three, P, Q, and D, or you can calculate by VI, and we got 2401 VA, okay. Now yeah, this is the equation for the waveform. Okay, let's revisit this power factor, but now in 3D form, okay. This is our previously known power triangle. Now, because we got another component, that's the D, we got S there, okay. Let's move into power factor. Now, we got all this. Where is the power factor now? Okay, displacement power factor is still the same. It's P divided by S1, and that is the cos phi, okay. That displacement power factor, not power factor anymore. Distortion power factor, this is a new kind of power factor. It's the ratio between S1, fundamental apparent power, and S, the final apparent power, okay. True power factor is P compared to S, okay. And when you see this, you know that P over S will be equals to P over S1 times S1 over S, because these two can be cancelled out. And you know that true power factor equals to displacement power factor, our cos phi, times distortion power factor. Okay, so if as okay, another thing is THD. We already know that THD is total harmonic distortion. Total harmonic distortion, as you know, is a harmonics component divided by the fundamental component. Right now, harmonics component is D. And when you divide by S1, because S1 is the one that contribute by the fundamental component, you can get THD by D divided by S1. Okay? And because of that, we have another formula for distortion power factor, S1 over S. You can also get that by 1 over square root of 1 plus THD square. Okay, as recap, let us see this. Okay, so P, you already know P will be equals to V I fundamental cos theta, cos phi. Okay, Q is always be V I fundamental sine phi. S1 is V I fundamental. D equals to V I harmonics. Okay. S is VI total. Okay. Of course, you can know as well that this equals to P squared plus Q squared plus D squared with square root. And can be also be S1 squared plus D squared square root. Okay. Similar to this S1, this will be equals to P squared plus Q squared square root. Okay. And now for the power factor, okay, we have ratio between P and S. P over S now is our displacement power factor, which equals to cos phi. Okay, and we got D and S fundamental. This is our THD, total harmonic distortion. We got S1 over S as our distortion power factor, or you can get this from distortion power factor from THD. Okay, if you want to get it, then distortion power factor, how do I write this, equals to distortion power factor equals to 1 over 1 plus THD square with square root over there. Okay, what else? What did I miss? Okay, finally, the one that we have been learning all this time, which is P over S. This is the new true power factor. Okay, so all this, okay, you need to understand the concept of all this, then it should be okay for you. Okay, you don't have to remember. This is just power triangle, but now we got another plane for that power triangle. Okay, that's all for this video. Head up to our column for exercise and quiz. Bye.